Welcome to the fifth lecture in Electrical Engineering Fundamentals. In this lecture, we will talk about the mesh current method, which is a powerful circuit analysis technique like the node voltage method discussed in the previous lecture. We will begin by introducing mesh currents. Then we'll discuss the application of the mesh current method with dependent sources and some special cases. We'll also compare between the node voltage and mesh current methods, and finally we'll solve some problems. As we previously discussed, the mesh is a loop with no other loops inside it. A mesh current is the current that exists only in the perimeter of the mesh. Mesh currents satisfy Kirchhoff's current law. That is, at any node in the circuit, the mesh current both enters and leaves the node. In the mesh current method, we apply Kirchhoff's voltage law to every mesh, taking into account the voltage drop in the direction of the mesh current and the voltage drop or rise of other mesh currents flowing in the same or opposite direction. All of these points will be further clarified in the following examples. In example 1, we need to use the mesh current method to determine the power associated with each voltage source. We then need to find the voltage across R2. We begin by noting that we have three meshes. We can call this one mesh A, the second one mesh B, and the third one mesh C. The current flowing in the first mesh is IA, the current flowing in the second mesh is IB, and the current flowing in the third mesh is IC. When we apply KVL, we should note that the voltage drop is always in the direction of the individual mesh current. That is, when we apply KVL to the first mesh, the voltage drop across R2 is in the direction of IA. However, the voltage drop across R2 when we apply KVL on the second mesh will be in the opposite direction, that is, in the direction of IB. The same thing applies for the third mesh. The direction of the voltage drop across R4 when we apply KVL on the third mesh will be in the direction of IC, but it will be in the direction of IB when we apply KVL on the second mesh. When we apply KVL on the first mesh, we'll get the following equation: minus Vx plus R1 times IA plus R2 times IA minus IB equals to 0. Here the minus sign for IB comes because it's flowing in the opposite direction of IA. The second equation we get when we apply KVL on the second mesh, where the equation is R2 times IB minus IA plus R3 times IB plus R4 times IB minus IC equals to 0. And finally, the third equation is R4 times IC minus IB plus R5 times IC plus Vy equals to 0. Solving equations 1, 2, and 3 for IA, IB, and IC, we get IA equals to 5.6 amps, IB equals to 2 amps, and IC equals to minus 0.8 amps. To find the power flowing through Vx, we know that IA is flowing in the direction of the voltage rise. So the power equation is written as P equals to minus Vx times IA equals to minus 224 watts, which is less than 0. This means that it's being delivered. For Vy, we know that IC is flowing in the direction of the voltage drop, so the power equation is written as P equals to Vy times IC equals to minus 16 watt. A negative power means that it's also being delivered. The voltage across R2 is written as V out equals to IA minus IB times R2 equals to 28.8 volts. To analyze circuits with dependent sources using the mesh current method, the same previous approach applies. However, in this case, the constraint equations of dependent sources are added to the mesh current equations. This will be illustrated in the following examples. In this example, we need to use the mesh current method to find the power dissipated in R4. We begin by noting that we have three meshes, mesh 1, mesh 2, and mesh 3. Applying KVL on mesh 1 yields the first equation, which is minus 50 plus R1 times I1 minus I2 plus R2 times I1 minus I3 equals to 0. The second equation is found by applying KVL on the second mesh, where we get R1 times I2 minus I1 plus R4 times I2 plus R3 times I2 minus I3 equals to 0. The third equation, by applying KVL on the third mesh, we get R2 times I3 minus I1 plus R3 times I3 minus I2 plus 15Ix equals to 0. We have three equations and four unknowns: I1, I2, I3, and Ix. The fourth equation is found by expressing the current controlling the dependent voltage source in terms of mesh currents. That is, Ix equals to I1 minus I3. This is the fourth equation needed. Solving these four equations for I1, I2, I3, and Ix yields I1 equals to 29.6 amps, I2 equals to 26 amps, I3 equals to 28 amps, and Ix equals to 1.6 amp. The power dissipated in R3 is found using the following equation: P equals to I3 minus I2 squared times R3 equals to 16 watts. Now we will discuss two special cases in the mesh current method. The first one is when a branch includes a current source that is not shared with another mesh. In this case, the mesh current method is simplified since one of the mesh currents will be known. In the second case, we'll have a current source in a branch that is shared between two meshes. In this case, we can combine the meshes to form a super mesh. When we write the mesh current equations, we remove the current source and avoid this branch. This will be clarified in the following example. In this example, we need to use the mesh current method to find V out across R1. We begin our solution by noting that we have three meshes: mesh 1, mesh 2, and mesh 3. We also observe that we have a current source in a branch shared between mesh 1 and mesh 2. In this case, we can neglect this branch and treat mesh 1 and mesh 2 as one super mesh. Applying KVL on the super mesh, we get the following equation: minus V1 plus R1 times I1 minus I3 plus R2 times I2 minus I3 plus V2 plus R5 times I2 plus R4 times I1 equals to 0. Applying KVL on the third mesh, we get R1 times I3 minus I1 plus R3 times I3 plus R2 times I3 minus I2 equals to 0. The third equation we get from the branch containing the current source, where we have I equals to I2 minus I1. Solving these equations for I1, I2, and I3 yields I1 equals to 1.75 amp, I2 equals to 6.75 amps, and I3 equals to 1.25 amps. The voltage across R1 is given by V out equals to R1 times I1 minus I3 equals to 1.5 volts. Now that we have learned about the node voltage method and the mesh current method, the question is, when should we use the node voltage method or the mesh current method? There is no clear answer for this question. However, if the circuit contains supernodes, then the node voltage method is preferred. If the circuit contains supermeshes, then the mesh current method is preferred. We should check for the number of essential nodes and the number of meshes to check which method will give us the fewer simultaneous equations to solve. In example 4, we need to find the power dissipated in R4. If we were to use the mesh current method to solve this problem, then we would need to solve for 5 simultaneous equations, since this circuit has 5 meshes. However, it would be simpler to use the node voltage method, since we have only 4 essential nodes. We begin the solution by defining V1, V2, and V3 with respect to the reference node 4. At node 1, we have the following equation: V1 minus VA over R1 plus V1 over R2 plus V1 minus V2 over R3 plus V1 minus V3 over R4 equals to 0. At node 3, we have this equation: V3 over R6 plus V3 minus V2 over R5 plus V3 plus VB over R7 plus V3 minus V1 over R4 equals to 0. At node 2, we have V2 equals to 50 Ix, and for the dependent voltage source, we have Ix equals to V3 minus V1 over R4. These are the 4 equations obtained. Solving equations 1, 2, 3, and 4 for V1, V2, V3, and Ix yields V1 equals to 62.5 volts, V2 equals to minus 11.75 volts, V3 equals to minus 8 volts, and Ix equals to minus 0.235 amps. The power dissipated in R4 is equal to Ix squared times R4 equals to 16.57 watts. In example 5, we need to find V out. Solving this problem using the node voltage method would require solving 3 simultaneous equations, excluding the equations related to dependent and independent sources. However, it would be simpler to solve this example using the mesh current method, since we noticed that we have two current sources shared between two meshes. We can combine all three meshes into one mesh. Applying KVL on the super mesh, we get minus V1 plus R1 times I1 plus R2 times I2 plus R3 times I3 plus 0.8 Vy plus R6 I3 plus R5 I2 plus R4 I1 equals to 0. The second equation comes from the dependent current source constraint, where we have 0.4 Vx equals to I2 minus I1 and Vx equals to I3 times R3. The equation from the independent current source is I equals to I3 minus I2. We also have the equations from the dependent voltage source, where Vy equals to minus I2 times R5. These are the first three equations obtained, and these are the remaining two. Solving these five equations for I1, I2, I3, Vx, and Vy, we get I1 equals to 2 amps, I2 equals to 12 amps, I3 equals to 12.5 amps, Vx equals to 25 volts, and Vy equals to minus 90 volts. Vout equals to V1 minus I1 times R1 plus R2 equals to 173 volts. In this problem, we need to use the mesh current method to find the power delivered by the voltage source as well as the power dissipated in R4. We begin by noting that we have three meshes. The first one is mesh A with current IA. The second one is mesh B with current IB. And the third one is mesh C with current IC. Applying KVL on these meshes, we get for mesh A minus V plus R1 times IA minus IC plus R2 times IA minus IB equals to 0. For mesh B, we have R2 times IB minus IA plus R3 times IB minus IC plus R4 times IB equals to 0. And for mesh C, we have R1 times IC minus IA plus R5 times IC plus R3 times IC minus IB equals to 0. Solving these equations for IA, IB, and IC, we get IA equals to 6 amps, IB equals to 4 amps, and IC equals to 2 amps. For the voltage source, we know that IA is flowing in the direction of the voltage rise, hence the power equation is written as P equals to minus V times IA equals to minus 600 watts. Since the power is negative, it means that it's being delivered. So we write that the power delivered by the voltage source is equal to 600 watts. The power dissipated in R4 is given by P equals to IB squared times R4 equals to 240 watts. In problem 2, we need to use the mesh current method to find how much power is being delivered to the dependent voltage source. We begin our solution by noting that we have three meshes, mesh 1 with current I1, mesh 2 with current I2, and mesh 3 with current I3. Applying KVL on these meshes, we get for mesh 1 we have minus V1 plus R1 times I1 minus I3 plus R2 times I1 minus I2 plus V2 equals to 0. For mesh 2 we have the following equation: minus V2 plus R2 times I2 minus I1 plus R3 times I2 minus I3 plus R4 times I2 equals to 0. And for the third mesh we have R1 times I3 minus I1 minus 3Vx plus R5 times I3 plus R3 times I3 minus I2 equals to 0. The constraint equation for the dependent voltage source is given by Vx equals to R3 times I2 minus I3. Solving these equations, we get I1 equals to 4 amps, I2 equals to 3 amps, I3 equals to minus 1 amp, and Vx equals to 12 volts. For the dependent voltage source, we have P equals to minus I3 times minus 3 Vx equals to minus 36 watts, which is less than 0. This means that the power is being delivered by the dependent source. Hence, the power delivered to the dependent source is P equals to minus 36 watts. In this problem, we need to use the mesh current method to find V out. We begin our solution by noting that we have three meshes: mesh 1 with current I1, mesh 2 with current I2, and mesh 3 with the current I3. Applying KVL on these meshes, we get for mesh 1 minus V plus R1 times I1 minus I3 plus R2 times I1 minus I2 equals to 0. For mesh 2, we have R2 times I2 minus I1 plus R3 times I2 minus I3 minus 40 Ix equals to 0. And for the third mesh, we have R1 times I3 minus I1 plus R4 times I3 plus R3 times I3 minus I2 equals to 0. For the dependent voltage source constraint, we have Ix equals to I1. Solving equations 1, 2, 3, and 4, we get I1 equals to minus 1 amps, I2 equals to minus 1.5 amp, and I3 equals to minus 0.5 amp. V out equals to I1 minus I2 times R2 equals to 20 volts. In problem 4, we need to find the power dissipated in R2 using the mesh current method. We begin the solution by noting that in mesh 3 we have a current source not being shared with any other mesh. In this case, we already know I3, which is equal to minus I. Applying KVL on the remaining meshes, we have for mesh 1 minus V plus R1 times I1 plus R2 times I1 minus I2 plus R6 times I1 equals to 0. And for the second mesh, we have R5 times I2 plus R2 times I2 minus I1 plus R3 times I2 plus R4 times I2 minus I3 equals to 0. Solving equations 1 and 2, we get I1 equals to 2 amps and I2 equals to minus 4 amps. The power dissipated in R2 is I1 minus I2 squared times R2 equals to 72 watts. In problem 5, we need to use the mesh current method to find IY. We begin the solution by noting that in mesh 2 we have a current source that belongs to a branch not being shared with any other mesh, from which we know that I2 equals to I equals to 30 amps. The same applies for I1, which equals to 0.25 Vx. Applying KVL on mesh Y, we get minus V plus R1 times IY minus I2 plus R2 times IY plus I1 equals to 0. And also we have an additional equation for the dependent current source constraint, from which Vx equals to R2 times IY plus I1. Solving these equations, we get IY equals to 10 amps and Vx equals to 40 volts. In problem 6, we need to find the power dissipated in R3 using the mesh current method. We begin the solution by noting that the independent current source I belongs to a branch shared between mesh 1 and mesh 3. In this case, we can combine these two meshes into one super mesh. Applying KVL to this super mesh, we have minus V1 plus R4 I3 plus R2 times I3 minus I2 plus R1 times I1 minus I2 equals to 0. Applying KVL on the second mesh, we have R3 times I2 plus R1 times I2 minus I1 plus R2 times I2 minus I3 minus V2 equals to 0. The equation from the independent current source is I equals to I1 minus I3. Solving these equations, we get I1 equals to 7 amps, I2 equals to 6 amps, and I3 equals to 5 amps. The power dissipated in R3 equals to I2 squared times R3 equals to 36 watts. In problem 7, we need to find the power delivered by the current source. We begin our solution by noting that the current source belongs to a branch shared between mesh 1 and mesh 2. We can combine these two meshes into one super mesh. Applying KVL to this mesh, we get the following equation. Minus V1 plus R1 I1 plus R2 I2 plus V2 equals to 0, and from the independent current source we obtain I equals to I2 minus I1. Solving equations 1 and 2, we get I1 equals to minus 1 amp and I2 equals to 1 amp. The voltage across the current source V is given by V equals to V1 minus R1 I1 equals to 35 volts. The current is flowing in the direction of the voltage rise, hence the power equation is written as P equals to minus VI equals to minus 70 watts. Since the power is negative, it means that it's being delivered. Hence we write the delivered power is equal to 70 watts. In this problem, we need to find the power delivered by the current source. We begin our solution by noting that the current source belongs to a branch not shared between any other mesh, from which we know that I3 equals to I equals to 4 amps. Applying KVL on the first mesh, we get minus V plus R1 times I1 minus I3 plus R2 times I1 minus I2 plus R4 times I1 equals to 0. Applying KVL on the second mesh, we have R2 times I2 minus I1 plus R3 times I2 minus I3 plus 30IX plus R5 times I2 equals to 0. And from the dependent voltage source, we have Ix equals to I1 minus I3. Solving equations 1, 2, and 3 for I1, I2, and Ix yields I1 equals to 9 amps, I2 equals to minus 6 amps, and Ix equals to 5 amps. In order to find the power delivered by the current source, we need to find the voltage across its terminals V1. In order to do that, we apply KVL on the outer loop, where we have minus V plus V1 plus 30Ix plus R5 times I2 plus R4 I1 equals to 0, from which V1 equals to minus 10 volts. The current in the independent current source is flowing in the direction of the voltage drop of V1. Hence, the power equation is written as P equals to V1 times I equals to minus 40 watts, which is less than 0. This means that the power is delivered. Hence, the power delivered by the independent current source is equal to 40 watts. As always, if you have any questions or concerns, please contact me. Thank you.